geometric Langlands correspondence.
All right. So let me remind you what's going on. The starting point was a Riemann surface X. And we were interested in doing some kind of Langlands correspondence. And because there are so many flavors, let me actually add a bunch of qualifiers to this. So this is at least once to have it all on board. So first of all, this is obviously, I'm going to say that this is like the function field case, because obviously, well, functions. Secondly, it should be clear that, that's a big thing. So we're doing global Langlands correspondence rather than trying to work with things on a small disk. So if you ever need to specify this, this would be global. And also, there are no ramifications, so everything kind of behaves nicely all over the curve, or Riemann surface, so this is unramified. And obviously, this is, so what we are doing is geometric, so maybe I should add geometric somewhere. I'm not sure if that's still linearly ordered. Anyway, there's also geometric floating somewhere. And for now, we'll also stick into the group GLN, although this will change soon. So that's, I believe, if you say all these words, that pretty much, maybe I should also say in the RAM settings at some point. So to say that I'm looking at D modules rather than local systems in some other sense. Anyway, so this is just to define what the area we're working with, and the two main players are the moduli of rank n bundles on X, and the moduli of local systems, also rank n. And as pointed out last time, by local systems, I understand bundles with flat connections. And so this correspondence, the conjectural correspondence, is supposed to assign to a local system. I guess I was using L in my first. Let me try to keep my notation consistent with my talk rather than with everybody else's talks. So L goes to port L. So the input is a local system. The output is a D module on the space of bundles, the stack of bundles. And it's supposed to satisfy a bunch of properties, namely, there's this Hecke eigenproperty, so it's supposed to be special in some sense, and this was partly explained last time, and I'll say more about it today. Then it's supposed to, you're supposed to, in some sense, get a basis in this category. So this family should form a basis. And again, this is mentioned slightly. And I'll say more about it in a moment. And finally, well, I guess you can say probably much more, but one of the things that I'm not going to talk about at all is compatibility with the Eisenstein series, so compatibility with parabolic induction, if you like. Let me just put it on the board, and then I'll never come back to it. Maybe I will, but anyway. So, all right. So this is a short reminder of what's going on. Now let me actually focus on this second point. And again, this is something that appeared yesterday, but not in my talk, so let me refresh your memory. So basically, to say that something forms a basis, a fancier way of saying it is that this you get an isomorphism between the standard vector space and the vector space where you want the basis. And so, and this is maybe the most convenient way to formulate this as some kind of geometric version of isomorphism of vector spaces, which is going to be an equivalence of categories. And so, in order for this equivalence even to state, even to define something that's supposed to be an equivalence, we need to think about the dependence of the output on the input. Namely, it's supposed to depend algebraically. So this additional requirement is that this Hecke eigen objects should form a family parameterized by local systems. So this should be a family, let me say LS, family of D modules of D of Bahn modules. So, in other words, what does this mean? This means, let me denote this family by fancy art, so that this is supposed to be a quasi-coherent sheaf on the product of the two stacks. And it carries a flat connection in the direction of one of the factors, but not in the direction of the other factor. So this, in other words, it's an OD module. So it's an O of LS tensor D Bahn module. All right. So, and if you really want some low-tech analogy, you can think of this as a kind of change of basis matrix corresponding to this basis. And now, the condition that it's a basis means that this change of basis matrix actually defines an isomorphism. So it's invertible. And this just geometrically, this amounts to the following. So this family, so we get a functor from, this is my notation for the category of O modules on local systems to the category of D modules on vector bundles. And so, and this is kind of standard push-pull. So we'll look at the product, which is where this OT lives. There are two projections. And the functor that we consider, well, I'm going from here, so this will be pullback tensor with this OT and then push forward. I'll get to this, but yes. So, and so the statement, so finally I get to actually state the conjecture, is that that this functor is supposed to be an equivalence or very close to it. So I guess I didn't get to state it. I guess I can state it precisely, but it's known to be false. So the naive geometric Langlands conjecture would say that this is an equivalence. However, the point is that it's not, I mean, it's not too wrong. Okay, so now let's go back to details. Everything here is supposed to be derived. So when I'm writing this, I really mean what people would normally write as d quasi-Koch of local systems. Similarly, this is the derived category of d modules on Bahn, and all the functors are derived. So, well, fortunately for pullback, I guess I don't have to worry, but tensor product, if necessary, if things are not flat, you have to derive it, and push forward has to be derived, definitely. So, in fact, I mean, even going back to this basic construction, if it so happened that it doesn't normally happen, but in principle, I wouldn't be too scared if it turned out that automorphic D module is not actually a D module, that this Hecke eigen D module is not a D module, but a complex. I mean, I can deal with this. It's okay. So this is first remark. So maybe let me just put it. So derive everything. Just to keep this in mind. And the second thing is that if you want, so as long as you're working with individual Hecke eigen objects, it doesn't really matter that much whether you're in the world of D modules or in the world of perverse sheaves. Now, if you want to deal with families like this, which is necessary to formulate such conjectures, you pretty much have to work with D modules, or at least it's much more clear how to state this in the world of D modules. All right, so any questions? Now, all right, I feel like I'm pretty much done the most important thing in this series of talks. Got this on the board. Of course, I was too slow, so somebody had it on I guess a few people had it on yesterday. Anyway, so now let me say a few words about what happens if we leave this world of GLN and go to other groups. Actually, let me say one more thing about GLN. If in case it's not clear, this is a conjecture. It's not a theorem. So unless there are, in fact, very few cases where this is completely proved. And again, one was discussed last time when n is equal to 1. Then this is a particular case of the Fourier transform constructed by Lamont. And past that, there are very few cases where it's actually completely worked out. And by few, I don't mean like n equals 2. Rather, I mean n equals 2, particular curve, and particular kind of, maybe some other modifications. And I want to say that it's very close. I don't want to say that it's close to being proved when n is equal to 2. but the things that are proved almost, it's almost like this bunch of lily pads that you can hopefully use to get from one side to the other. When for general n, the distance between lily pads is a little bigger, but at least all the lily pads are still there. When I start talking about arbitrary group, there are we're not sure if some lily pads are even in place. Anyway, so other groups. So the first thing, maybe the first new thing is that if you are dealing that two groups should actually appear. So suppose that G is now a reductive group over the complex numbers. Let me consider its Langlands dual. Of G, then the new feature is that now we will be dealing with vector bundles and local systems for these two different groups. So the players will be bund G, which is the, I shouldn't have said vector bundles. Anyway, so you probably know what I mean. So we have G bundles on X and local systems for the Langlands dual group. Check local systems on X. I guess you can say that now the two sides of the conjecture are even further from each other. Other than that, the general shape of the conjecture remains the same. So now, let me just fill it in here. So now ought is supposed to be, let me say is, but of course everything is conjectural. So it's parameterized by these local systems, and so this is a family parameterized by local systems of D modules on G bundles. And the conjecture is that, well, we can construct such a family with nice properties, and roughly speaking, that it gives an equivalence from between the two sides. So I'm drawing the arrow from the Galois side to the automorphic side, but since it's an equivalence, you can go either way. And maybe just, I will be repeating myself, but so let me just say that there is certain interesting symmetry, which is not accidental, that on the one side, we look at, so to say, topological objects on X, and then we consider some geometric category associated with it. So this thing uses connection, and then we study on the space of such objects just quasi-coherent guys. Here it's the other way around. We look at some geometric objects, and then we study topological, essentially topological category, where by topological I mean something to do with bundles with connections. So it's geometry of topology versus topology of geometry. All right, so here's the statement. Now the things become slightly more interesting if you actually try to now go back to the first property that you want. So, and ask, well, what do you want from this? So what is the Hecke eigenproperty in this generality. And so informally, just to remind you what happened for GLN, the Hecke eigenproperty had to do with change in a vector bundle at one point. So you looked at a vector bundle, then you considered all possible ways to mess it up in a particular way, to modify it in a particular way at one point, and then essentially by integrating over these different ways, we could define an operator, or more properly a functor, on this category. So in order to play this game for arbitrary group, we need to know how to modify G bundles where G is no longer GLN. So this is what I want to talk about now. So the big question is how to modify G bundles at a particular point. So the point will be fixed until the very end. Now, just the basic idea of modification, so first of all, what exactly do I mean by modification? That I can say very precisely. So a modification now just means that you have two G bundles and an isomorphism between them away from this single point X. So if you like, you can say that you started with the same bundle on the punctured curve and then you extended it in two different ways across the puncture. Now, because we are no longer working with GLN, these modifications are slightly less explicit. So, but at least it's more or less clear what they are going to be classified by. So they are classified by double cosets. Let me actually not try to fit it here. They are classified by double cosets of this shape, where K is the field of Laurent series, O is the ring of Taylor series, and Z is a coordinate at this point. So in other words, we are just saying that if we trivialize this, both of this F1 and F2 near this point, then such an isomorphism will be given by an element of G, probably with a pole, and then changing the two trivializations makes us mod out by these guys on both sides. So, for example, when I was talking about GLN, I was looking at this particular kind of, so to say, minimal modification, where you had a vector bundle and then just enlarge it by a little bit. And so the minimal modification corresponds to a particular class, minimal particular double coset, which is something like Z111. So it's so to say an element that is invertible over Laurent series, and it fails to be invertible over Taylor series, but by by the smallest possible margin. All right. Now, the main thing that you don't necessarily see when you work with minimal modification, if you work with such minimal modification only, is that, well, roughly speaking, I want to say the following, that for different types of modifications, we will get different different ways to modify G bundles, and accordingly different operators acting on different functors acting on this category. But we don't want to restrict ourselves to just looking at a single type of modification. Rather, we want to consider weighted combinations of different modifications. And so classically, this would lead immediately to the idea of Hecke algebra. So classically, we would now say that let's say my ground field is now finite, so that I can actually count points, and then I can consider the Hecke algebra, which is simply the vector space of finitely supported functions. I'll just say that we look at functions from this double coset space to, say, C, and it carries, well, it sort of inherits the convolution product from functions on the group. So it's an algebra under convolution. And so the statement, our setup, so to say, is that at each point we have some kind of this kind of Hecke algebra. These Hecke algebras for all points, they act on the object we are trying to analyze. So we have these automorphic forms with actions of these Hecke operators, and we are trying to analyze this representation. So we're looking for eigenvectors. We will be looking for eigenvectors with respect to these guys. But of course, we will do everything geometrically, because that's what the talk is about. So right. So geometrically, we will look at our vector space will turn into a category, Hecke category, which is, basically I want to say D modules on this double coset, but since I don't want to think about this, it's technically easier not to think about, take this double quotient in two steps, namely consider one-sided quotient first, and that's a really important object. So you probably recognize it as the affine Grassmannian. And then the category, let me denote it by fancy H, that we are dealing with, it's going to be the category of D modules on the affine Grassmannian. And these D modules are supposed to be equivariant under the action of G of O. So basically, because it's this one-sided quotient still carries an action of G of K, and inside this G of K, we have the subgroup of kind of nice loops, and we consider D modules that are equivariant, equipped with an equivariant structure under this action. So, and again, this is done for technical reasons. Informally, you can think of this as D modules on double cosets. So there are some technical issues here about these are not maybe the most traditional objects in algebraic geometry. These groups are kind of infinite dimensional, but it turns out that this is not very far from some familiar guys. And so once the technicalities are taken care of, you can turn this, well, first of all, you can define this category. And more importantly for us, you can define convolution on this category. So H carries a monoidal operation, if you like. You can call it tensor product. So H is a monoidal category under convolution. That I'll denote by star. So this is a bifunctor from H to itself. And again, essentially this is because G of k is a group. Or another way to explain it is that if you think of this as some kinds of modifications, then you can try composing modifications. If you have two modifications done in a sequence, that's supposed to be a modification again. All right, so this is part of our structure. Well, and the vital piece of data for us is that this category actually acts, this monoidal category acts on the automorphic side of the geometric Langlands correspondence. So since this is important, let me put it here. So H acts on D mod bun G. And again, modular technicalities, this is simply because you can modify G bundles. So in other words, let me just informally, here's what I want to say. So if we consider all possible modifications, that is to say pairs consisting of two G bundles and an isomorphism away from this point, then you can, there will be two projections to Bun given by forgetting. Let me just say like this. So you can send it to F1, which is in Bun. You can send it to F2, so the second projection, which is also in the same place. Well, I guess I should be saying Bun G just. And then you can also just remember the type of this modification, or in other words, this is actually the same as restricting this whole thing to the neighborhood, formal neighborhood of the point X. So let me just say that this is, the map tau is the type of this modification as an element in the double, in these double cosets. And now, if I want to, if I have an element in H, and I want to act by it, so if I have something in H, and I want to act by it, well, I want to say I pull it back here and use it as a kernel. So let me, so this is going to act as pullback of M. So, and then I shouldn't do this. So if you have what we think of as a D module on double cosets and we want to act by it, it's going to act as this functor. And once again, everything is derived. All right, and so I want to say now that our goal, if you want to, one way to look at the geometric Langlands conjecture is that we're analyzing this category as a module over this monoidal category. Now, in order to, why is this good, by the way? So what's just, the point is that, I mean, this is hard. So, the difficulty is that this thing is global. So when we look at band G, it knows about geometry and about geometry of the curve. And, I mean, who knows what the curve actually looks like? So these kind of categories, well, this stack itself and the category of D modules on it, it's going to be pretty tricky. On the other hand, when we're doing modifications, we forget about the curve entirely and just work in the neighborhood of one point, and that's supposed to be easy. So roughly speaking, our point is we can understand this H pretty well and then use this understanding to maybe analyze what goes on here. So this is our plan. And by the way, now I can fulfill the promise made last time. Now, if you want this structure, if you want to be able to modify bundles, you cannot restrict yourself to semi-stable things. Because when you're modifying things, there's no way to keep track of semi-stability. You might start with something semi-stable, then mess it up at one point. It's no longer semi-stable. So if you want this structure, you must work with stack rather than moduli space. All right. Now, now we get to actually, I think, the only non-trivial statement of today's lecture, namely the geometric Satake equivalence. So unlike everything that came up to this, well, I guess there were some lemmas here, and there were big conjectures. Now there's a theorem. So and geometric Satake equivalence describes the structure of this category. So it somehow fulfills our expectation that local picture should be simpler. So geometric Satake equivalence So this is a theorem. So proved by Ginsburg and Mirkovic-Vilonen, and then there are various versions, improvements, so you probably should be able to pick your favorite type from among many. Anyway, so the claim is that, I just want to make sure I'm not missing anything. So the claim is that this category is actually equivalent, almost more or less naturally, to the category of the representations of the Langlands dual group. So representations of, well, algebraic representations of Langlands dual group. And this is, I want to say, this is the first case where we actually see the Langlands dual group, or rather maybe I should say the first theorem where we actually see the Langlands dual group in this story. Up to this point, it was all conjectures, and now we see that this, that it appears kind of naturally. You start studying something. You start studying something related to the group, and the answer is expressed in terms of a different group. Now, a few more comments about this. First of all, this isomorphism is supposed to agree with the convolution. So this is an isomorphism as monoidal categories. Otherwise, it wouldn't be too useful, because if you don't remember, if you just use direct sum, this category is not very interesting. Yes?
Is this just finite dimensional?
It depends on what kind of D modules you consider. So basically, if you consider holonomic D modules, then yes, you just get finite dimensional representations. In some situations, it might be more useful to look at the infinite sums. And the point is that because the group is reductive, any representation is actually direct sum of finite dimensional ones. So we don't really lose much by looking at finite dimensional representations. Other questions? Right. So this is one point, and kind of painful, at least for me, thing to say, is that here it's probably better to work with abelian categories rather than with derived categories. Now, so let me just say that this is for abelian categories. And if you like abelian categories, that shouldn't actually be a problem. If you prefer working with derived categories, there is a version of this, but it's harder for derived categories, but it's harder to formulate. So it's not kind of, you don't get just an isomorphism between the derived category on the left and the derived category of the category of representations on the right. So it's something more subtle, and so I'll stick to the abelian categories version. Okay, now what is important about this theorem is that in some sense it's required to even formulate that conjecture that we're after, this geometric Langlands conjecture. Because somehow to normalize geometric Langlands conjecture, to say what we expect of it, we need to know what we want to impose a Hecke eigenproperty on our objects. And now this Hecke eigenproperty should tell you how objects in the Hecke algebra act, or in the Hecke category, if you like, are supposed to act on the particular automorphic objects that we construct. So the construction for the Hecke eigenproperty must include a recipe that tells us what eigenvalue a particular element in this category is supposed to have on a particular object we are constructing. Well, in order to give an answer to this, we need to know what this category is, and that's where the Satake equivalence comes into play. And in fact, miraculously, it even translates this category into the terms that we find acceptable on the Galois side of the geometric Langlands. Now let me just state this carefully. So first of all, so this Satake equivalence, it's, can I do this? It's used to state the Hecke eigenproperty, used in the following Hecke eigenproperty. Now, what is the Hecke eigenproperty? Just, again, because there was so many objects at different times, so let me remind you what's, roughly speaking, what this is supposed to say. So we were looking at a particular local system for the Langlands dual group. And this, we wanted to give us an object, a D module, maybe a complex of D modules if we are not lucky, on band G. Now, we want this complex to be an eigen object, an eigencomplex, for the action of H of this Hecke category that acts on band G. So now we are supposed to, given an object, let me call it M, that's what I've been using on that board. So given an object in the Hecke category, this, well, it acts via this functor on the category of D modules. So we can take, and let me use convolution for the action as well. So we can act by it on this automorphic guy. And it's supposed to be, well, it's not supposed to be invariant. It's supposed to be an eigenobject. That is to say, it's supposed to scale, which in this geometric world just means that it gets tensored by a particular vector space, maybe complex of vector spaces. So we're supposed to have this for some vector space lambda m, which plays the role of eigenvalue. So we now got to the point where eigenvalue is a vector space. Yes. So this is the eigenvalue of m on this. Now, this line just says that we want to construct an eigenvector. Now, to normalize the correspondence, I need to tell you what this eigenvalue must be, and the answer should depend on everything on the board, that is to say, on M and L. Now, in fact, it is even more, well, we can make things more interesting if we remember that there is also hidden dependence here. We fixed a point. So we fixed a point, so we had a Hecke operator at that particular point, so we get a vector space associated to this particular point. Now, if the point is allowed to vary, we will be able to get a vector space will vary, the eigenvalue will vary. And so if the point varies, this thing will be a local system on X. Well, that tells you how the eigenvalue varies with points. So in fact, so now I'm erasing the part where we're modifying at one point only, because we no longer do this. We're allowed to change points. So as X varies, this eigenvalue is actually now a local system of vector spaces on X. Okay, and so once again, the prescription for the Hecke eigenproperty should tell us how to construct a local system of vector spaces, starting from a local system for the Langlands dual group and an element in the Hecke algebra. an object in the Hecke category more precisely. Now, if you use that, now there is the time to use the Satake equivalence. So this object corresponds to a representation of the dual group. And so, and of course, if you have a representation, we can, if you have a representation of the dual group and the local system under this dual group, there's a natural way to construct a local system of vector spaces. You just take this local system and apply the representation to it. So, well, so means so we can write this. So this word makes sense. So this is our part of the Hecke eigenproperty, or if you like, it's an axiom of the geometric Langlands correspondence. And once again, as promised, Satake equivalence plays a crucial role in it. Okay, does it make sense? Kind of. Now, let's now review what happened last time from this new, using this new approach. So, last time, when G was GLN, we were looking at a particular, only at one particular modification. So a minimal modification, that is a particular coset, a double coset. So it's like, let me just say that this minimal modification is an element in G of O, mod G of K, mod G of O. So now if I want to think in terms of the Hecke algebra, then instead of looking at this element itself, I would rather look at the d module of delta functions. I would look at sort of a delta function sitting at it. So let me call it delta of M for minimal modification. So is an element in this Hecke, this geometric Hecke algebra, this Hecke monoidal category, which, according to the Satake equivalence, is supposed to correspond to a representation of the Langlands dual of GLN. Now, the good news is that this is GLN again, and the minimal modification is so natural that it shouldn't really come as a big surprise that the thing that corresponds to it is the most natural representation of GLN, namely the standard representation.
Do you see a quotient by the center? I mean, so the dual isn't really GLN, it's GLN mod Zn. Isn't that show up?
So why is it GLN? I mean, this is kind of a very, now for GLN is self-dual, at least in this world. Now, if I wanted SLN, then it would be more interesting. Yeah. Okay. So, any other questions? All right. And so now, because this, to apply a standard representation to a local system of vector spaces doesn't do anything, and so you can see that this axiom actually becomes the Hecke eigenproperty, the simpler Hecke eigenproperty for GLN as formulated last time. So, but of course, at least technically, even if G is GLN, you have many different, more complicated ways of modifying vector bundles, and this will still produce, which will produce somehow more interesting eigenvalues. For example, you might have to take the symmetric power of your local system or something along these lines. Okay, so does it make sense? Any questions? Now, I don't know, let me say a few words about what goes on, what will happen next time, and next time is the day after tomorrow, if I remember correctly. Well, so by now I feel that I at least put something on the board that's it's precise enough that it has a chance of being true or false. Now, of course, the downside is that it's actually false. So we gave it a chance and it failed us. So, but it's false in some. So the failure is basically due to the fact that it somehow works best in the situations where local systems are irreducible, and it needs correction at points where, well, it needs correction when you are looking at local systems that are reducible. So, and in fact, so one way to deal with this is to actually artificially introduce some setup where all local systems would be reducible, and then this naive statement, I don't know if it's still on the board, if I'm lucky, nope. Anyway, the naive statement in this form can actually sometimes be verified, so it doesn't fail. Now, my goal for the next time is to explain exactly how we know that this, well, exactly maybe is too strong a word, but to explain a bit about why we know this to be inconsistent in general, and also to say what corrections are necessary in order to, well, to again make a precise statement, and now one that actually has a chance of being true. Thank you.